Hola, muchas gracias por la invitación. As you know, I'm Brazilian, but I'm speaking English, sorry. My Spanish is not that good. But when the time of the questions, if you speak very slowly, I think I can understand. Okay, so I'm going to talk about Atlantic hurricanes. I'll first give an overall view of the climatology so that everybody's in the same pace and everybody knows the same, so that then we can go in more details about our work. So let's start about looking about tropical cyclones. So although I'm going to focus the Atlantic, we actually have tropical cyclones everywhere, and the Western Northern Pacific is the region we have most of the tropical cyclones in the world, and the most intense too, you see by the color here. You here in Mexico affected by both the Atlantic and the Eastern Pacific. This time I'm just talking about the Atlantic. In different regions of the world, we have a very different climatology. The Atlantic you can see as a very narrow climatology, very peaked, while in the Eastern and Central Pacific is much wider. And you have in the Western Pacific, you actually have typhoons year-round. The peak is usually late summer, early fall, as is in the Atlantic. So here in the Southern Hemisphere, we tend to have most of the tropical cyclones in January, February, March. So now focusing on the Atlantic. So this is your typical hurricane tracks in the Atlantic. A lot of them starting in the main development region, starting near Africa, a lot of them recurving, some of them going through extratropical transition, and then coming even to affect Europe. So as I said, the peak of the hurricane season in the Atlantic has a peak around September 10. So we're getting close to the peak of the hurricane season. We usually have about 11 named storms, so they become tropical storms. About 6 of them become hurricanes, and about 2 of them became major hurricanes. This is your mean for many years. There is a huge variability of the number of storms per year. So what I'm showing here is the number of tropical cyclones per year, starting in 1851 until 2017. The ones in blue are your tropical storms. They get a name, but they don't reach hurricane category. The ones in green are your hurricanes, category 1 and 2. Your red are category 3, 4, and 5, your major hurricanes. So there is a lot of variability here, focused in 1950 to 2017, when you have better data. We know that in this part of the record here, we are missing a lot of storms because we only know there were storms when they make landfall and there are people leaving, and there's nobody leaving their place. We wouldn't know that storm, or if you have your ship going under that storm, and then you would know. Otherwise, you would miss that storm before satellite area. Why we have such a big variability from year to year? So one of the big reasons is El Niño Southern Oscillation, or ENSO, and we usually have this warming anomalous warming in the Pacific, and then people always ask, how does the warming in the Pacific affect hurricane activity in the Atlantic? So what happens is that we have the typical circulation, Walker circulation, in the normal years, and you have here in the Atlantic that we have a lot of storms happening here, but then what happened in the El Niño conditions, you have descent over the Atlantic. And because you have descent of the Atlantic becomes harder, and at the same time there's change in the winds. So here you have your typical profile of winds in when you have a La Niña year, and here in El Nino years. And you see that you have a much higher vertical shear over the Atlantic. The difference of the winds in the bottom, the top of the troposphere is higher. So you can imagine if you're trying to form a tropical cyclone, those winds will just keep on breaking your convection, so it must be harder to form. And that's why we seem to have fewer tropical cyclones in the Atlantic over in El Nino years. Doesn't mean that we do not have them. On that, there will be no chance of having a major hurricane with the landfalling in El Nino years. It's just the probability is smaller. And also will depend on how strong your El Nino is, where the warming is, if it's more central, if more eastern Pacific, and that will affect the patterns of the winds, that will affect where you're having a convection or not. So this is looking at the stability. So besides the shear, this is a measure of disequilibrium, and you see it goes very nicely together with your Nino 3.4, with the measure of your El Nino. And you see when you have an El Nino, you have less disequilibrium, it's more stable. So if it's more stable, it's harder to form the tropical cyclones. So it's this combination of the vertical shear and higher stability that makes harder to have Atlantic hurricanes in El Nino years. And here you can see the effect of that. So here is your Atlantic hurricanes from 1950 to 2017 El Nino years. And here in La Nina years, you have here 80 hurricanes and here 127 hurricanes. So it's not that you do not have hurricanes. You do have, but you have many more in La Nina years. And here, if you count how many storms are passing in each location and subtract your, and then you divide by the number of years, you have a density, and you subtract them, you see that in La Nina years, you tend to have many more storms in different regions of the Atlantic basin. So if you look here now, going back to the same plot I had before, but now calling by El Nino and La Nina, and you see in green are years that we call neutral years. They're not El Nino, they're not La Nina. And here in red, your El Nino years, and in blue, your La Nina years. This is your median, and here's 25th percentile and 75th percentile. So you see that most of the blue years, or La Nina years, they are above the median. And most of your red years, your El Nino years, they're below median. But that's not always the case. You see here that this is an El Nino year, and you still have a high activity. So that's what I always have to remember, is that the probability of having a season like that increases, a below normal season increases in El Nino years, and but it's not always the case. And the Atlantic's not the only place that's affected by El Nino. Here is a map of indices that we look at how well we can have tropical storms, like there's a potential for formation of storms. So if you look at the anomalies for El Nino and La Nina years, and you see here the increase of Atlantic activity in La Nina years that I talked before, but you see that the Eastern Pacific actually the opposite. They always have this opposite behavior because the way the Walker circulation changes. And so this is very well known, this bimodal behavior. And here in the Western Pacific, you have something different. What you have there is a shift, or where the typhoons form. They tend to form closer to the equator and closer to the dateline in El Nino years, and closer to the Asia continent in La Nina years. Why is that important? Because these typhoons that form here, they end up having much longer tracks, and they end up very much more intense typhoons in El Nino year. While the ones that form closer to the coast of Asia, they will end up having shorter tracks and will be weaker typhoons. And also will impact, they have a big difference of where they make landfall in El Nino and La Nina years. So it's not so much number of typhoons, but where they form and how intense they're going to be and where they're going to make landfall. So besides El Nino, we have, the whole soup of whatever letters you want is your letter soup of climate modes. So you have your, ENSO, and then we have the Madden-Julian oscillation, the quasi-biennial oscillation, the Indian Ocean dipole, the North Atlantic oscillation. So you have all kinds of climate modes, and they all influence tropical cyclones, and in different ways in different regions. And here I'm going from shorter time scales to longer time scales. So we have the equatorial waves here that are happening synoptic to subseasonal time scales, and here we have your decadal variability here. So all these modes influence tropical cyclones in different ways. So looking in the Atlantic, the second most important mode of variability for Atlantic hurricane activity is the Atlantic meridional mode, which is basically a bimode of that you have between the Atlantic and the tropics, and here more to the north. So when you have here warmer in this region and cooler here, you tend to have all these hurricanes forming in this region here. When you have the opposite phase of this dipole in the Atlantic, when you have this colder SST in this region, you see that these are your hurricanes. You have much fewer hurricanes happening. And also you see that they actually happen in more to the north, and here are more in the main development region. So you have this, how the pattern of the Atlantic sea surface temperature will also influence your hurricane activity. So these things then go together. So you have your El Nino, and then you have your Atlantic meridional mode happening together. So this is a very nice study looking how they combine. So here you have how the El Nino is happening. So here's El Nino, ENSO neutral, and La Nina. And here you have the Atlantic meridional mode, the AMM negative, neutral, and positive. So what we talked before, we have La Nina, you tend to have more Atlantic hurricanes. So this is here. This line here, your La Nina. But you have to see what's happening with the Atlantic as well. So if you happen to have both the La Nina and the Atlantic is in your positive mode, then it's when you have your very, very active years. So, but now if you have a La Nina, but the Atlantic is in the opposite phase, although it's a La Nina, we do not have, actually here tend to have fewer hurricanes than normal. That's why it's not only always a 1-to-1. Look here in the El Nino, usually we have fewer hurricanes. But if you have also the Atlantic is in positive, you can actually have a slightly positive activity. So all these climate modes combine, and you have to see how their combination will affect hurricane activity. And then when you look at the hurricane tracks and separate them in clusters, you can actually then, for different clusters, we see which modes of variability are important. For instance, these tropical clusters are the ones that have the strong El Nino signal, while an AMM signal as well. So you can see here the two tropical clusters, you have the El Nino here signal and also the AMM dipole here. While when you look at these subtropical clusters, you actually do not see a signal for the El Nino. And what we see here is actually an influence of the NAO, the North Atlantic oscillation. So different types of tracks are affected for different types of climate modes. So here in the case of the Gulf of Mexico, we have a high influence of the Madden-Julian oscillation, but not so much of the El Nino. What about the quasi-biennial oscillation? That's a very interesting case because you have in the stratosphere this quasi-biennial oscillation, and for a while it seems that, so these are looking at correlations with tropical cyclone activity, various measures of tropical cyclone activity. And you see that in the 80s, we actually have, very clear relationship of the quasi-biennial oscillation and tropical cyclones. But then suddenly, this correlation is gone. So in the 80s, Bill Gray, when he's first talking about doing seasonal forecast, they were using the quasi-biennial oscillation as one of their predictors for their seasonal forecast. And they were right. The relationship was there, but then this relationship disappeared. So was this a statistical fluke, or was there something that changed in the atmosphere? That's a very good question. So people are now looking at other connections, the QBO with the Meridional oscillation, and they are seeing this kind of behavior as well, that sometimes they are very well correlated and other times they are not. So talk about forecasts. So in the early 80s, they started the first tropical seasonal forecast. The first ones actually were in the Australian region by Neville Nichols, who first saw this relationship of ENSO and Australian TCs. And he just very simple linear regression and developed a forecast. And then Bill Gray in the Colorado State University started developing, and as I said, he used both ENSO and the QBO. And the Caribbean sea level pressure. So these are what started in 1980s. By 2007, then we have all these forecasts for the North Atlantic. So we have the statistical ones like Bill Gray. They have some dynamical ones. That's what the ECMWF started. What does that mean? They're looking at their climate models, and they're running their forecast, and they're counting the storms in the climate model, and they're seeing if they're having above normal, normal, or below normal activities. And then you start having various, like the NOAA outlooks, they're starting having many more. And I helped develop this one at IRI. We started looking at dynamical forecasts for tropical cyclones using their forecast as their seasonal forecast system. Today, we have each one of these is one different forecast for the Atlantic, for all different centers. This is from 2018. This is what we end up happening in number of hurricanes. And you can see, how the different models did for that season. And if you ask me, I think we have done enough of developing forecasts like that. I was talking with Christian, we have to go beyond that now. We want to start developing forecasts for number of landfalling hurricanes, more, measures that are actually interesting, because if we think about it, there are years that we have a lot of hurricanes in the middle of the Atlantic, but they don't make landfall. So we don't even know that the season was like that. So I don't think we should keep on doing this more and more, slightly different version of this forecast, but we should improve what we can do in terms of forecast. What's the scientific challenge of doing seasonal forecast is ENSO. So when I was looking at my forecast when I worked at IRI, the years that my forecast failed were the years that the IRI ENSO forecast failed. So, and I think most of the forecasts are based on that. So, doesn't matter how fancy or the machine learning and whatever I'm going to try to do a seasonal forecast of tropical cyclones, if my ENSO forecast is not good, my tropical cyclone forecast is not going to be good. So there has been a lot of improvement in the ENSO forecast. The skill of the dynamical models have been improved, especially during the spring barrier. The spring barrier is when we go from one the period of you have an El Nino, and then you can have either a La Nina or a neutral or another El Nino year. So that's the hard part to predict. Once you have, the El Nino starting, then it's easier to predict. So this is what is called the spring barrier. And so that's why when you look at this tropical cyclone seasonal forecast, they have, in the Atlantic, they have very little skew before June, because that's when ENSO is not, we don't know what ENSO is going to be. Once ENSO is there, then they have much more skew. So the skew of all the seasonal forecasts is based on the ENSO forecast. So if you want to improve your hurricane seasonal forecast, you have to improve your ENSO forecast as well. And as I said, there is the NAO as well, and some of the more subtropical storms are influenced by NAO. And until some years ago, we would say, there is no skew in predicting NAO. But recently, people from UK have insight that actually they have some predictability in the forecast in the NAO in the winter. So maybe one day there is some skew in the forecasting NAO as well. And of course, then there's this whole decadal variability. So we're talking about the decadal variability. We have the Atlantic multi-decadal oscillation, and there has been a lot of discussion in the scientific literature if that's really an oscillation or not. There's people that say that's basically what you see, this part that you have, the Atlantic is cold, and you have fewer Atlantic hurricanes, is basically because you had a lot of aerosols in the Atlantic. While more recently, Amy Clement and colleagues have seen that you can have the AMO without a role for the ocean circulation. So this is a current debate in the climate community. What exactly is the AMO? And if it's a combination of all these things or not. And this would influence a lot of your Atlantic variability. So you see here, this is a measure of tropical cyclone activity in the Atlantic. You see clear that you have a lower, below normal period here for many years. And then you can, since 95, have active. But you're trying to understand what exactly is going on here. It's what we are. Okay. But because there is this relationship of the AMO with tropical cyclone activity, people have started doing multi-year forecasts for Atlantic tropical cyclone activity, saying the next 5 years how the Atlantic is going to be. Of course, until now, we are looking at in hindcast. We need a few, like 10 years or 15 years to see if these forecasts are any good. But people are starting to put them out. And then you have, for instance, here, 2017, you see that your season is not equally busy. You have a part of the season that you have a lot of storms happening at the same time. Here, for instance, you have the infamous ones, Irma, Maria, happening at the same time. And part of it is the Madden-Julian oscillation. So the Madden-Julian oscillation, now we're talking about intra-seasonal, so activity within a season. So you have a few weeks, a couple of weeks that you have a lot of tropical cyclones. And the Madden-Julian oscillation starts in the Indian Ocean, and you have this very active region. And then as it moves to and has, besides it, a region that you have downward motion. So here you have dry, and here you have very wet, and it moves eastward. And as it moves eastwards, it modulates tropical cyclones. How does it work? So here you see the Madden-Julian oscillation propagating eastward, and this is what the very famous index, the Wheeler and Hendon. And so these are the different phases of the MJO. And if you look here, the OLR, and as it propagates eastward, this is the OLR in the contours, and you have here in colors a Genesis index. And you see that when you have the active MJO, you also have more tropical cyclones having. The normal is high, more than you have in that season. And it would be very interesting to be able to forecast that. Which part of the season you have more tropical cyclones? And that's not only in the Atlantic or the Southern Hemisphere, you can have globally impacts of the MJO. Until some years ago, we could not do any forecast because there was absolutely no skill in forecasting the MJO. The climate models couldn't even simulate the MJO. But very recently, here you have the ECMWF having very high correlation and being able to forecast the occurrence of the MJO. And other systems are behind, but you see a lot of them are starting. So if we are able now to have some skill in the MJO, now what the first thing we have to know, if these models are able to simulate this relationship of the MJO and the tropical cyclones. So that's what, so here you have the activity of the tropical cyclones propagating eastward in the Southern Hemisphere in the observations, and here you see in the Bureau from Australia, the Chinese model, and the ECMWF. So they're kind of doing it. And we can, here is a way of measuring skill that we came up. This is the different phases of the MJO, and here the different basins. And here the diagonal, you see the propagation of the MJO. And as the is active, you see in the red and yellow colors is where you have more tropical cyclones, and the off phases, regions, you have fewer tropical cyclones. So this is the same thing that I showed before, but I'm now showing all phases of the MJO and all basins. So this is what your MJO modulation is. So here is what the ECMWF model does. So the ECMWF, of course, here I just have one realization of the observations. Here the ECMWF model is running every 10 days with lots of ensemble, so my signal is much stronger here. And you see clearly that in the diagonal here have a increase in the tropical cyclones in the MJO system, and in the regions that you have descent, you have fewer tropical cyclones, very clear in the MJOs, in the ECMWF, and the correlation between those two patterns is 64%. So here we are. It is able to reproduce this relationship. So we start looking at what do we need to now make forecasts of tropical cyclones and subseasonal timescales. So say in the next 2, 3, and 4 weeks, we are going to have a lot of tropical cyclones or not. So we basically came up with 3 things. This is analyzing all these models in this S2S data set. It's a WMO sponsored project that lots of centers are putting their data in. And basically there are 3 things that we need for a system to be able to have some skill in forecasting tropical cyclone subseasonal timescale. The first thing is this. The model has to be able to forecast the MJO. If your model can't forecast the MJO, forget. You can't not forecast the tropical cyclone subseasonal timescale. The second thing, the models have to be able to do the seasonality correctly, because you are trying to forecast the anomalies of that season. If your model is not able to forecast the seasonality right, you are not going to have skill. And the third is what I showed before, that relationship between the tropical cyclones and the MJO in the model. So clearly there are 2 models that stand out in these models we look at, is the ECMWF and the Bureau from Australia. And now we're trying to understand what the other models can do to do as competitive as they are. So something that we're talking about, and maybe you guys are interested because about volcanoes. And so there's a few papers saying, well, once you have a volcano, then you have fewer tropical cyclones in the Atlantic. But you have like 3 volcanoes in your analysis, so it's hard to swallow. But then there's another paper saying, actually, in the paleo data, we also see some signal like that. So what are the issues? First of all, we have very few volcanic events. Second of all, the analysis was only in the Atlantic, but if you have a big volcanic signal, you shouldn't have tropical cyclone activity changes only in the Atlantic. Why? The volcanic signal expressed in the whole world. And then, most important, these volcanic events happen together, El Nino. So you have here a gong, and you have Nino 3.4, and you have your volcanic eruption here. One El Nino, one volcano. El Chichon. Here you have your volcano, here you have your El Nino. Pinatubo, same thing. So how these studies could tell what was El Nino and what was volcano? And so that's what the work that we just got published. We look at observation reanalysis, we could not separate El Nino and volcano because we just have very few volcanoes. We looked at the CIMIP-5 and the N-Carl ensemble and tried to see, not in the tropical cyclones themselves, but proxies of tropical cyclones. And basically what we see that what's shown here, and it's well known actually from the CIMIP-5 models, the model response to volcanoes is too strong. They really respond, the climate is, so that ends up being this response that we have in the potential intensity, which is a proxy for tropical cyclones, is not realistic because the climate models are too. And when we look like synthetic tracks, is like way of making tons and tons of tropical cyclones for when you have too few data. And so we have those tracks with and without volcanoes. And again, there is no significant change. Doesn't mean that the signal is not there. It means that so far, the data we have is not clear. But we got a model that have, very strong volcanoes. This is a Tambora strength and volcanoes. And then we ran that for many, many ensembles. And then we start having a signal that's interesting. Then what you have, you see, this is the shift in precipitation here, less precipitation here, more precipitation. And what you see in some proxies for tropical cyclones, that they have the same shift. So, but this is for Tambora simulations, strength simulations, many, many ensembles, and then you have this signal. So that's why it's very hard to see when you have weaker volcanoes, and also will depend on the timing of the volcano eruption and everything. So this is something I have been started doing, and it's, I think, very fun looking how all these things combine. Okay, finish up with climate change. How climate change influences tropical cyclones. So you have the increased surface temperature, increased atmospheric temperature, and of course you have more humidity in the atmosphere. So it's not, all these things influence tropical cyclones in different ways. So it's not straightforward to say, okay, we have higher system temperature, we have more tropical cyclones, more intense tropical cyclones. So we have really to understand. So how could hurricanes change with global warming? Could be the number of tropical cyclones per year, could be their intensity, their duration, the precipitation associated with tropical cyclones, where they happen, could be all these things. We just had this week a new review of tropical cyclone activity projections appeared at BAMS. We're done by a team chosen by the WMO, and we all worked for many months together to put this. And this is the main things that we, as a team, think we have medium to high confidence in the projections. First thing, sea level rise. What else is more clearer signal than increase in temperature, sea level rise? We know that's going to happen, okay? So even if it's nothing happened with your hurricanes, if you have sea level rise, what's going to happen? You have exactly the same hurricane, the storm surge will start in a lower level, so you have higher inundation levels. This is like a no-brainer. We know that's going to happen, okay? Then, tropical cyclone precipitation. We know regular precipitation, what's going to happen with extreme precipitation. Because you have more humidity in the atmosphere, what we have? More extreme precipitation. The tropical cyclone associated precipitation is the same. So we expect to have an increase of the extreme precipitation associated with tropical cyclones, as well as the median precipitation associated. Tropical cyclone intensity, we also expect an increase, having the median of the intensity as well as the proportion of Cat 4 and 5. Okay, then we get to the ones that we have now medium to low confidence. Why? Because we could have different models are doing different things, we don't understand the processes as well, and things like that. So then we have the decrease in tropical cyclone, for instance, which a few years ago would be in the other category. Now we start having a few models that actually are increasing with tropical cyclone frequency, and we don't understand exactly why. So now, because we have this dichotomy, we have less confidence in this decrease that before was very robust result. There has been a lot of work doing the polar expansion of tropical cyclones, especially in the northwestern Pacific. And there's in some papers an increase in the number of 4.5 tropical cyclones. So this is a little difference, just having more or the proportion of them being more. So this is a little less confident that the proportion increasing. And there's one paper looking at the slowdown of the tropical cyclone translation speed in the current data. In the projections, that's not very robust at all. Different models are doing different things. So that's what we expect. But can we say anything already about that we have a tropical cyclone trends or not? So what's the problem here? Here's all extreme events here from PNAS. And here, which ones here we have talked about the understanding of how climate change affects this extreme event, and here the confidence in the capability of the models. Okay? So which ones we know better? Extreme heat. Okay? So here it is. We understand well, the models can do well. Where are tropical cyclones? Here we have tropical cyclones. Okay? So we kind of understand some of how tropical cyclones respond, but the models are not very able yet to, especially 5 kind of models, to simulate tropical cyclones. And a lot of that is because of data. So here we have how well the models are able to simulate different classes of events, the quality of the record, and the mechanisms. So here, extreme cold events and extreme heat events, we know very well, the models can simulate, and also data quality is good. Temperature, we can measure that. Then we come here to tropical cyclones. So the models are not doing as well. The quality of the data is pretty bad. The Atlantic is the best one. Other parts of the world is really bad. And how we understand this, like medium. There are a lot of things we don't understand yet. So that's why it's very hard when every time a hurricane happens, people call me, the report, and say, is this due to tropical through climate change or not? So what are the issues? There's also a large amplitude of the fluctuations. I showed you how many tropical cyclones have year by year. So for us to have a trend, in the clear trend in the tropical cyclones, that trend has to be bigger than the variability to be a significant trend. And then, because the records of tropical cyclones are short and the quality is bad, they have large error bars. So for me to see a trend, the trend has to be bigger than your variability, and also it has to be bigger than your error bar. So there's a lot of uncertainty. Doesn't mean that's not happening. What means it's very hard to say that's already happening. These are two different things. When I ask someone, say, oh, can you say that there's a signal in tropical cyclones in the intensity or not? What my problem is, can my data pass all this quality control or not? Doesn't mean that's not happening. Maybe it's just because our data is not good enough. And this is just an example. So if you just look at global mean temperature and SST in the Atlantic, if you just do the counts of tropical storm in the Atlantic, I see, oh, there's a trend in the mean temperature, there's a trend in the Atlantic. There's my very naive way, okay? But we know, for instance, that we missed the very short storms. So imagine the storms that last 2 days in the middle of the Atlantic. Do you think we capture all of them? Of course not. The weak ones, the short-lived ones. So if you do an easy statistical adjustment, then with here, just considering tropical storms and up, excluding your tropical depressions, which are the weak ones that we know we might have missed. So you see that the trend is already smaller. Now if we do the tropical storms and also exclude in your data the storms that are less than 2 days, then the trend is gone. And most important, our best data would be the US landfalling storms, and there is no trend there. Actually, you'll be actually a little decreasing trend. So that's why it's hard to make a very convincing argument that we already see that in the data. Doesn't mean that's not happening. It's just our data has so many issues, and the variability from year to year, that's hard to say. And then when you look at, they're all having a lot of studies looking at intensity and seeing here, say, okay, this is the trend in intensity. And in 2005, these 2 papers appeared and was like a lot of splash because they were exactly when Katrina happened, and say, yes, we already see, this paper were basically saying we already seen a trend in the Cat 4 and 5. And then this follow-up, this paper seeing an increase in the quantiles, the higher quantiles intensity in 2008. But this is the kind of data that we are looking at. So there's a lot of variability from year to year. A lot of that we don't know, especially intensity. One thing is knowing when there is a tropical cyclone. One thing is now knowing if your tropical cyclone is Cat 4 or Cat 5. Remember, they just changed the intensity of Michael that happened last year from Cat 4 to Cat 5. So if you're now going for each of these storms in the middle of the South Indian Ocean and knowing how well that intensity is, that's why it's very hard to know. These error bars are quite big. And there's a lot of variability. So this is the kind of data we are trying to deal with. So more recent studies here. So here, Klotzbar and Lancy went back to the Webster paper in 2005 and continued the data, just redid the same analysis with 10 more years of data. And you still see that increase that Webster saw, but you see it has been flattened here. And here's this Bhatia look at different data sets, and all of them have some increase in the highest quartiles, but not all of them. So more recently, what people start doing and doing attribution study. So getting one storm, for instance, Harvey, and saying, what's the question that journalists asked? Was the storm due to climate change? What's the problem with that? Climate change do not cause tropical cyclones, okay? Tropical cyclones are part of this climate system. What could climate change do? It can change the characteristics of that storm, okay? Make it more intense or make it more rainfall. So that's what people are looking now. So here are 3 different studies looking at Hurricane Harvey and looking at how much climate change contributed to the rainfall of that storm. And here are different methods. Here is a modeling data analysis. Here is completely statistical data just with observations. And here a combination of modeling and data. And so what they could come up is like 6% of the rainfall of Harvey was increased because of climate change. 6%. And here you have 19%. And here we have 15%. So that's where the state of the art of this science is. So depending on the way, the method you're using, you get in different results. But these are the kind of contributions that we could see in climate change in specific storms. But then there came this other work here, just published too, and what they did is they looked, besides climate change, they look at urbanization. And we know that's important. So we know there's a heat island, you have cement, you have asphalt, that will also influence your rainfall in the Houston area. So here they ran their model, without urbanization and without climate change, and they ran their model with climate change and with urbanization and both things combined. And what they show is that in different reservoirs, different creeks and bayous in Houston, they could see that a signal both of climate change and urbanization. So when now you're doing these attribution studies, you can't just forget about land change uses. And now there's the first case of people making these attribution studies before the storm even happened. Just saying that in the case of Florence, a lot of the rainfall would be increased before or for climate change, and people put this out even before the storm happened. What can we do? People are doing to improve this problem with the data not being as good. There are a lot of work in the National Hurricane Center doing the reanalysis of all the hurricane data. Unfortunately, that has been only focused in the Atlantic, and they're actually finding hurricanes that they didn't know existed. Just looking at weather maps and looking at ship track data and other kind of things. That should be done through all around the world. And then archival studies, looking at historical data, people can reconstruct a lot of the hurricanes. Of course, you're doing like now, if you're going to the 1600s here, there are a lot of uncertainty. And that's where people were living in that region. Or what a lot of people do in Lamont, where I work, use geological proxies. And here you can imagine you have a hurricane coming, there is a beach, and there is a marsh, and there is some dunes. And when you have a big storm surge, that storm surge, you bring a lot of sand to your marsh. So then you do a coring, you see this overwash of sand. And then you can go and you can see, how old that sand is, and then you can connect that to specific hurricanes. And if you do that in many regions around the world, and then here the hurricanes but then you can then start seeing hurricanes in regions that you didn't know in those regions because there are not people living there. Of course, you can't do that in Miami now because instead of having marshes and beaches, you're having, high rises. The other way is look at caves, the stalagmites. Stalagmites also have very strong hurricane signals, and then we can look here are the known hurricanes. Then you have a big stalagmite. You can go back in time and start reconstructing hurricane activity. Corals, the same kind of thing. They can also record hurricane activity. So they're very important for the Australian region. So this is my summary. So Atlantic hurricane is modulated by various modes of climate modes in all different time scales, from subseasonal and shorter to decadal time scale to climate change. Now we have forecasts of the Atlantic in seasonal time scales, subseasonal, multi-year time scales, based on those relationships. The projection of tropical cyclone activity have been very consistent for many years. That we have, storm surge problem, the intensity. The only thing that has changed recently is the tropical cyclone frequency. And the trends, we have problem that basically is a data problem. Not that, it's not a non-believer of climate change. It's just, we have a lot of data problems here. And we hope that with paleotempestology, we can improve our understanding of past hurricane activity. Thank you.
Thank you, Suzana. Les voy a pasar el código de nuevo, si quieren hacer las preguntas por escrito en lugar de hacerlas en voz alta. El código era 98 49 28. ¿Okay? Lo repito, 98 49 28. Ok, entonces, es MENTI, MENTI, tilatina.com. ¿Okay? Y entonces esas las recibe Ivonne. Entonces abrimos al público.
Bueno, buenas tardes. Tengo una pregunta. Pone usted...
Pues sí, puede ser despacito porque la doctora habla portugués, así que entiende castellano, pero no habla.
¿En qué unidades se mide los ciclones tropicales? En la energía acumulada en los ciclones, ¿en qué unidades se mide?
So ACE, accumulated cyclone energy, is not squared. So it's every time you have a hurricane, you get the wind speed and square. And then you add that for the whole season or for that cyclone. So it has both number for a season, is also duration and intensity, but because it's the intensity squared, is mostly related to intensity.
Thank you. Gracias.
Okay, thank you very much, Suzana, for this nice presentation. So you show us clearly that the MGO and the ENSO are very important to be modulated in the climate models to forecast the hurricanes, right? But my question is, how well are aerosols modulated into those climate models, given that, for example, here in the Atlantic, the Saharan dust particles, they might play a big role on that, right? So how confident are you guys on that? This is my first question. And the second one is this very nice paper that shows us about the importance of volcanic eruptions. So I didn't get the point, what is the main contribution from volcanic eruptions? Is it more the ash particles, the gases, or is something dynamical that I missed? So that's it, thank you.
Okay, I think the climate models can't do aerosols at all. They are very bad at it, especially in that short time scales. I don't think they're doing dust well, so I think clearly that's a big problem. And maybe that's why some of the forecasts are bad, because they're not doing the dust well. The volcanic aerosols, the idea is that when you have a volcanic eruption, you have the cooling in the surface and in the warming in the tropopause. And that warming, this difference, you can see the potential intensity, which is basically the theory for the intensity of hurricanes, is basically exactly at this difference. So you can see how if you have changes in that, you would tend to have changes in hurricane activity. So it's basically on the changes in the temperature profile. From the volcanic aerosols, which, as I showed, the CMIP5 models do very poorly. So, but that's what we have right now, you know. So there are these papers that are, so people saying that exist, so we went ahead to see how well they do it. So what I want to do in the future, first of all, a lot of these models are low-top models, and to do the volcanic eruptions well, you should do high-top models. If you really want to do the tropical cyclones, you also need to do high-resolution models. A lot of these studies, I was just looking at proxies, and people were just looking at proxies as well, so I think you really should look at the hurricanes themselves. And also, you should have interactive aerosols. A lot of them do not have interest. So I think there's a lot to do there, but I think some interesting things that's coming up now.
Thank you.
¿Otras preguntas? Okay. Les quiero comentar que por la seguridad de la traductora, tengan cuidado cuando tomen el micrófono y no lo golpeen, porque si no ella recibe un sonido muy fuerte.
Gracias, Suzana. This question is in English. You showed us two very important modes of variability for the Atlantic tropical cyclones, and one of them is the ENSO, and the other one is the AMM.
Mm-hmm.
And it was very interesting to see that this diagram where you show with these circles larger, when both modes combine and you get very high. My question is about if we know now that these ENSO and AMM are actually two very independent modes.
Well, Yes and no, because you know there is a known relationship between ENSO and the surface temperature in the Atlantic. So, but it's not that you only have the AMM when you have ENSO. So that you can have the AMM without ENSO, but when ENSO happens, also influence the Atlantic. So that's why it's hard to separate these things completely. And I like that study that I showed from Patricola, that was a modeling study, and that she did her model, because in observations we can't really do that. She did her model only forced with ENSO, and then she had her model only forced with AMM, and then she did her model forced with both. And that's where you get this. But in nature, all things are combined, so it's harder.
Ahora vamos a ir a unas preguntas que el doctor Carles va a leer.
Bueno, es una.
Ah.
Is from your analysis, which is the best for hurricane forecast and monitoring? I suppose the best model?
Well, monitoring, I don't know. So I think it depends on the time scales. I think the National Hurricane Center, put a very nice, but they use input from different systems. There has been a lot of discussion that ECMWF has been doing very well at that time scale and beats the American models, but I myself hadn't done that analysis, but has been a lot of discussion on that. In the sub-seasonal forecast, that's something that work I was involved in, and we looked at that. ECMWF is clearly an order of magnitude above the other models. But I think, it's in sub-seasonal forecasting, in seasonal forecasting, then it's something else. Then you have, it's harder to compare, and the sub-seasonal, that's a problem too. The problem is that people forecast different variables at different leads, at different lengths. So for instance, one forecast in sub-seasonal, how many hurricanes you're going to have in the next season, in the next 2 or 3 weeks. The other one does the probability of genesis over a certain the Gulf, part of the Gulf. So how do you compare these two forecasts? And how do you verify them? So the sub-seasonal forecasting is a very new type of thing that's happening. And I think one of the main things that will have to happen is the forecast will have to be uniform, if you really want to compare across agencies and what they forecast, their leads, their length of their forecast, and the variables. Otherwise, we really can't forecast. That's why we did this analysis, because it's this S2S database from the WMO, and at least we use the same variables, the same skew scores throughout all these models. But even that has a problem, because this was an ensemble of opportunity, as they say, so each modeling group give the data as they have. So each of those models had different resolution. The forecast had different frequency that they did the forecast. They did with different leads. So even that, it's not a clean comparison, because we are just using the data we have.
Thanks.
¿Hay otra pregunta? No. Ok, ¿alguna pregunta aquí en este auditorio? No. Ok.
Una pregunta. Cuando hacen sus modelos, utilizan, supongo, ecuaciones diferenciales, ¿verdad? De dinámica.
Modelos dinâmicos?
Ajá.
Quando eu não faço mais forecast, no. I don't do that anymore. But when I was at IRI, when I developed, we used, at that time was the ECAM 4.5 model, and that's what they used to run for their modeling system, for their seasonal forecast. And my contribution was, I went there and I tracked the tropical cyclones, and I tracked there for their huge hindcast to get the climatology of that model, and then I define what's the probability of each of the, in each of categories, and then I came up with the way of correcting, because the model have bias correction for the model, then to apply my forecast. So that's how I did it. Different seasonal forecasts using different methods. So the statistical ones, there are people that use regression. There are people now that, the big thing, the new machine learning stuff. There are people that use a combination of statistical and dynamical. So for instance, instead of going and finding the storm in your model, they just get the environmental fields that people use in their statistical model, and then they use that environmental field as their forecast of their statistical model. This is your statistical dynamical model. So different groups use different methodologies.
Con respecto a eso, entonces, cuando comparan sus modelos dinámicos con los datos estadísticos, entonces vi que como que no cuadran tan bien, ¿verdad? Pero esperen, es que bueno, también mostró diagramas box plot, y pues yo supongo que es porque hay datos atípicos, y los datos atípicos son los que no se consideran, pero si se consideraran con un modelo global, entonces yo supongo que podrían encontrarse, o sea, más similares a los modelos dinámicos, supongo, ¿no?
So when we compare the model skill, we are comparing observations. That's the first thing we want to compare. So it doesn't matter if whatever the other model is. The problem with the statistical models is that typically they cannot forecast a season that never happened before. So you get 2005, if you have trained your statistical model without 2005 in the Atlantic, and if you try to forecast 2005, no statistical model is going to do that. So while the dynamical models, the advantage is they do not that restriction. They can forecast a season that never happened before. And that's why they're used for climate change, because they are able to, just using the physics and dynamics of the atmosphere, to try to predict what's going to happen, and that can be things that never happened before. While with climate change, a purely statistical model doesn't happen.
¿Alguna más? También por escrito. Muy bien.
Sí. The question is, what kind of data will be the best for getting the trends in tropical cyclone activity in the Atlantic? Is there any project for improving the existing data?
So one of these is the one I showed, the reanalysis that Chris Lancey leads at the National Hurricane Center, and he has been doing that for many, many years. So he has a team, and they go decade by decade, and they reanalyze all this data, and they correct them and improve them. So that has been happening. Of course, then if you get more historical data and paleo data, you can use that as well eventually. So the problem is that if you want trends, for instance, the southern hemisphere, you do not have any data, basically, almost any, before 1980. So you have 30 years of data. So if you want to do a trend and you want hundreds of years of data, so you do not have that. So you're trying to use reanalysis, you're trying to use paleo to fill up these gaps, but if you ever have a perfect world that you have perfect data, that's very hard. That's why one of the things we do, I have involved in projects like that to do real risk analysis, we generate these synthetic hurricanes. So, for instance, we have a project that we did in Mumbai. Mumbai, in the historical record, has never been hit by a tropical cyclone. But there is a possibility, because they have tropical cyclone landfall north and south of Mumbai. So we use our model that generates synthetic hurricanes and the Carey Manuel MIT model, and we generate thousands and thousands of hurricanes in the Indian Ocean, the Arabian Sea, to see the chance of happening one that could affect Mumbai. And then we look at the ones that could be Cat 3 and 4 and 5. And then we look at the probability of that happening, and in in 100 years, in 500 years, and in 1,000 years. So that's one way to do it, is using these risk models that, that's how insurance companies do. insurance companies use this risk model to generate synthetic tracks. So, but their models are completely statistical, so they cannot handle climate change. The ones that we generate in academia, we also make them such that they can also handle climate change.
Thanks.
¿Alguna pregunta más? ¿No? Entonces agradecemos a Suzana por su presentación.
Thank you so much for being here, and thank you, Graciela, for the invitation. It was a pleasure to be here.
Ok, ¿dónde está la bolsita? Ya regalo.